Can you hear me?
Yes, I can.
Okay, good. I was having technical difficulties earlier, so I'm glad it's working. All right. Okay, are you able to see the Word document?
Yes.
Okay, good. All right. So I'm just gonna go ahead and start. I have to do this in a little unorthodox way. My document camera is acting up, so I'm basically gonna uh, type in using um, Word to help me go. So if it's a little choppy, I'm sorry, but at least it's something better than nothing. So that's kind of where we're at. If you have questions, just like we were in class, just go ahead, unmute yourself and ask your question. Otherwise, this is recorded, so we'll just go ahead and get going, okay? Perfect. All right, so 9.3 is the multiplication property, and it also uses conditional probability. So we have to look at conditional first so that we can actually work through your multiplication property. A conditional probability says that a probability will occur given that something has already occurred. Okay. So, for example, what is the probability that Savannah Tech will be closed given that Hurricane Milton was coming? So, when we're talking about conditions, that is what we're talking about. We have to have the first event happen in order for the second event to occur. And so we use this notation right here. So this little straight bar is the phrase given that. So what this probability here says is it says P, find the probability of, and it's event A occurring, given that event B had to happen. And so essentially what we are looking at is we're taking the probability that both A and B happen over the probability that B had to occur because that was our limiting probability. Okay. Now, for me, the easiest way to understand it is to look at the actual question. So we're going to go back to that spinner that we used with the addition property. And instead of it just being numbers, notice I've now added G's and R's. So G stands for green, R stands for red. And so our spinner now has two ideas attached. The first is that there are numbers, and the second is that there are colors. So what we want to do is we want to find the probability that we are going to spin an even given that we had to spin a red. So essentially what we are looking at is we are looking at for your probability of even given the probability of red simply means we're going to set up an equation, and that equation is going to be a fraction, and that fraction is going to be created by the probability of both over the probability of red. And the reason I know that it's red is because this is that second piece that we have. So in order to actually calculate what we're looking for, we have to know the individual pieces. So I have to know the probability of calculating my red first. And to do that, says again, I'm setting up my fraction. So to figure out my red, I have to look at in my spinner how many of those tiles are red. So we have R's that we're looking for, and you would count up the parts. So here we would have 4 of them were red out of my 8 spinners that I had. Okay. Now, the second part that we need is we have to have the part of both. And so we want to look at our spinner, and we want to look at, in terms of your spinner, which ones have both an even number and have an R. And so if we look at those, we have the 2 of R, we have a 4R, and so therefore we would have 2 of them out of my 8. So to set up the overall, when we're looking at the conditional of even given your red, we're setting up a fraction within a fraction. And so your numerator, again, is the probability of both. So this would be my 2 over 8. My denominator is the probability of just red. So this is 4 out of 8. Now the rule for fractions simply says if your denominators are exactly the same, then you ignore them. So I really have 2 over 4, which we would reduce down to 1/2. And this will follow the exact same rule we used in the addition, which is that you either have a reduced fraction answer or you give me its decimal answer. Okay, so your condition is going to be set up a little different, but that is essentially what we're doing. So you're going to have the probability you're looking for, given that a certain probability had to happen first. So in general, we're doing the probability where both are occurring, given that this first event had to happen on its own. Okay. So any confusion on the spinner question or kind of the beginnings of getting into what a conditional probability is?
Not for me.
Okay. All right, so if we move to this next question, this one is going to require a little bit more thought because we have a lot of information and we have to figure out what is the probability I'm after versus the condition that it's being held to. This is a 2-part question to pay attention to. So it reads, out of 300 applicants for a job, 212 are male. Of the male job applicants, 110 have served in the military. So the first question wants to know the probability that a randomly chosen applicant has served in the military given that he is male. So it is this piece right here that says given that you want to pay attention to, and that is the part that tells you this is in fact a conditional probability. So then you have to look at how is it written. And the probability that comes before the phrase given that is the probability of, quote, both. The probability that comes after is the probability of the condition. So here we have served in the military given that he is male, which means served in the military is my probability where both occur. We're looking for military male service members. And then the given that he is male is the condition we were bound to, okay? So here, when we think about what it is we're really looking for, we are looking for the probability that you are military given that you are male. Okay, so that is the conditional probability we're trying to calculate. In order to get there, says we have to separate our two probabilities into their pieces. So the first thing that we have to have is we have to have the probability that we were military. And that is found again by creating your fraction where your total goes to the bottom, and this total is 300 because I had 300 applicants. Now I have to look at, of those applicants, how many of them are going to be military. And what it tells me is that it says of the male job applicants, 110 served in the military. And so therefore, my military would be 110. Okay. Now at this point, I'm not going to do anything. I'm not going to reduce because I want to be able to work with my fraction as is. So I'm going to leave this and now look at my second probability that I need to have, which is the probability of male. Again, we are talking about a fraction, and just like before, my total is still 300. But of the information given, the only other number I have is that 212 were male. So 212 is what we've got. Now we have to set this up in your conditional probability. So my conditional probability simply says that we have to do the probability of my military over the probability of my male. Okay. And so what we're going to get here is that the probability of military given male is going to be set by, again, finding my fraction, where my top number is going to be my military. So this is going to be the 110 over 300. And my denominator is going to be my male, so 212 over 300. Just like before, my denominators are the same, and this is why we do not reduce unless you absolutely have to, and why you want to save your reduction until the very end of your problem so that you don't have to do more work than is required. And so here we can simply cancel out or delete out our denominator terms, which means we're stuck with 110 over 212 to be our fraction. And then again, like before, you would reduce your fraction all the way down or just simply give me its decimal answer to be the result. But this result right here was what we were looking for. So that would be the answer for your probability that your applicant served in the military, given that he was male. Okay. Now the second part adds in a new piece and a twist on your conditional because now we have a new number, and that number is 152. So if 152 applicants served in the military, the question says, what is the probability that a randomly chosen applicant is male, given that the applicant served in the military? So again, given that is what you look for. That tells you it's your conditional. And now notice the roles have reversed. Instead, our both probability has to do with being male, and the condition surrounding it has to do with serving in the military. So here we are now looking at male, given that this is military. So the roles have reversed. We still have to do the same thing we did before, which is we still have to set up your conditional. And so the way we're going to do that is in its reverse role from what we did up in here. So the first thing we're going to look at this time is we are going to look at the probability that we are male. And so to do that, we have to look at all of the information we have and figure out which value is being used. So in the entire problem, we have the number 300, which is the total. We have the number 212, which are male applicants. Now, if you think about that number 212, that number is just simply that you were male, meaning this number is going to hold both military service members and non-military service members. The number 110 is specific to military male service members. And since that's the condition we have to have in the second part, the probability of being my male serving in the military would be 110 over the 300. Okay. Now, the secondary or the partner piece is to find your military. So here my condition says I can't use anything else because I have no other numbers in the top, since we just talked about that 212 representing males that are both service and non-service members. So the only other piece of information we have is this number here, that 152. And this 152 are strictly applicants that served, which means this is going to encompass everybody, right? Both male and female service members. So since military is my condition, now we have that this is 152 over my 300. Now, just like before, we have to set up your conditional probability. So here, male, given that you are military, is set by, again, creating your fraction, where your numerator is the probability of being male, so 110 over 300, and your denominator is the probability of military, 152 over that 300. Since I did not reduce early, my denominators will go away on both, thus allowing me to reduce an easier fraction, 110 over 152, and then therefore either reduce it down or give the decimal answer. Okay. So are there any questions on this second example going back and forth between your conditions, i.e. one direction versus the other? Cool. All right, so what the conditional probability does is it leads us to be able to work into the multiplication principle. So for the multiplication principle, we have to look at what it is in its base form. So just like with the addition principle, use the word or, the multiplication principle here is going to use the word and. So we are looking now at event A and event B occurring, and that's how your conditional is going to come into play. Now, just like before, this is going to split into what's called independent and dependent events. Okay, kind of like how the addition principle had mutually exclusive and not mutually exclusive, right? Where mutually exclusive meant they share nothing, and not mutually exclusive meant we had sharing across. Independent events means the first event has no influence over the outcome of the second event. Dependent events says the first event has a direct influence over the outcome of the second event. Okay, so if we look at these examples here, this first one is the color of a car driven by 3 randomly chosen classmates. Okay, this is an independent event. Why? Well, for example, I drive a blue Acura RDX. Now, does the fact that I picked a blue car have any impact on whatever vehicle you pick to drive? I'm going to assume the answer there should be no, right? So it is independent because it doesn't matter what I chose, you're going to make your own decision. So the fact that I was, say, event A, where I picked my blue Acura RDX to be my vehicle of choice, has absolutely no influence on the fact that you drive whatever color and vehicle you picked. Okay, that's independence. Dependence, again, means there is an influence there. So if you think about the second question here, that a password is 6 characters long with no repeated characters, are the choices of consecutive characters independent or dependent? Because of this phrase right here, that there are no repeated characters, this means that these events are dependent because whatever choice I make for my first character is going to directly influence the choice that I can make for my second character. For example, if I started my password by making my first choice the letter R, then my second character could no longer be the letter R because I've already used it. Therefore, the pool that I had to pick from has reduced. And that is what dependent characters do. Okay. So with that, we have the two different ways that we see these formulas. So the first here is your independent formula. Your independent formula simply says you're going to take the probability of your first event and multiply it onto the probability of your second event and then get your answer. Okay. And then that's it. There's nothing more that's going to happen there. You just take them as two separate probabilities, but this time we are multiplying them together. Dependent events is where that conditional probability comes into play. And the reason for that is because, again, a dependent event meant your first probability had a direct impact on the outcome of the second. So in order to use your multiplication rule here, you would take your first probability and you would multiply it to the conditional probability of the second event. Okay, for example, if we were working with a deck of cards, if I reached into my deck and I drew a card and I kept it, then when I went to draw a second card, the total of my deck has changed. My first probability had 52 cards to choose from, but my second probability now only had 51 because I kept and held on to that card without giving it back. Okay. Versus if I take that same deck and I draw a card, but then I put it back in the pile. When I draw my second card, I still was drawing from 52 cards. So that's the difference kind of between an independent event and a dependent event. Okay. So just like with the addition principle, where we had to read the question and determine what we were doing, you have to do the same thing here. Only instead of looking for the word or, we're looking for the word and. Okay. Once you determine that this is a multiplication principle, you then have to determine, is this independent or is this dependent in terms of events? Because that is going to dictate how your second event is managed. So if we look at this first one here, we want the probability of choosing a heart and then an ace from a standard deck of cards with replacement. So there are two things here to pay attention to. The first is the word and. That told me that this was the addition, the multiplication principle. And the second is this piece here, which is the word with replacement. Now this with replacement part means that these are independent events. And so that's the first thing that you need to take away from, is that these are independent events, which means my first event has no bearing on the outcome of the second event. So what I'm doing here is I'm finding the probability that I'm going to get a heart and an ace. And to do that says I have to take the probability of getting a heart, and I have to multiply that by the probability of getting an ace. Okay? So when I look at my probabilities here, the probability of getting a heart is going to be 13 out of my 52. I then have to multiply that by the probability of an ace. And probability of an ace says I have 4 out of that same 52. Because once I drew that heart card, I put it back and then drew the ace card. So here, simply, you would multiply straight across the top and straight across the bottom. So you're going to end up with 52 over 2704. And then you would reduce this all the way down to a simplified fraction or simply give its decimal answer and then round however you're told to round. So again, as a refresher, the millionth space would be 0.019231. Okay. Are there any questions over an independent multiplication probability? Okay, so moving right along, find the probability of choosing a heart as the second card if the first card drawn without replacement was a queen. Now, this one is a little different because we want a heart as the second card. This is the piece that we needed to pay attention to because this one is actually a classical probability that uses the condition idea to get you there. The only probability we are looking for is that we are going to get a heart as the second card. And that's it. Now, this piece here that says without replacement, that is what tells us what our bottom number has to be, which means my first card drawn was a queen, but I'm going to keep that queen. So when I go to look at my actual probability creation, my denominator term here is not actually 52, instead it's 51. Now, how many hearts do I have? I have 13. And that's it for this one. Okay, so this one is using your multiplication probability as a guide and the conditional piece to frame what it is you're doing, but you're not actually going to do the entire multiplication part because of the probability you are looking for. Okay, any questions on that one? Okay, this third one or this next one right here is the exact same thing. Find the probability of choosing a heart as the second card if the first card drawn without replacement was also a heart. Okay, this one is what I like to call a double condition. And the reason for that is because if you think about the framework, again, we are looking for the probability of getting a heart as the second card. But my first card drawn was also a heart. So again, if I look at how this probability has to be put together, I'm still creating that fraction. Because of the without replacement, my denominator term is going to be 51. But my first card was also a heart, which means when I go to draw that second card, I only have 12 hearts remaining in my deck because I'm already holding one. Okay, so when we're talking about having a double condition, it means not only was my denominator term impacted, but my numerator was also impacted by the drawing of that first card. All right, this question here is one of the questions I like a lot, purely because it really does test whether or not you understand what dependent events are in terms of multiplication. So we want to find the probability that from a standard deck of cards, you're dealt two cards, the 9 of clubs, and then another number card. So here's the and. This piece right there is what tells you it was the multiplication principle. So the probability we are looking for is we are looking for the 9 of clubs and another number card. Okay. Now, this piece where we have another number card is a condition. And it's a conditional that says the first thing I had to do was draw the 9 of clubs because the 9 of clubs is a number card. And nowhere in this entire problem did we use the phrase with replacement. Okay, which means when I draw that 9 of clubs, I'm going to hold on to that 9 of clubs. So what we are really saying here in terms of my probability is that this is the probability of getting a 9 of clubs and the fact that we are going to get a number card given that you drew the 9 of clubs first. Okay. So we have to look at how is this going to be set up. So the first thing we need to know is the probability of getting the 9 of clubs. Well, the 9 of clubs says I only have one 9 of clubs in my deck and 52 cards that I'm choosing from. The second piece is I have to have my condition. This is a number card, given that we already did the 9 of clubs. So when I look at this fraction, because I'm already holding a card, my bottom changed and became 51 because my deck has changed. But the other thing to keep in mind is that I'm also already holding a number card. Since we know that there are 40 number cards in a deck, and I'm already holding one, it means my numerator has to be 31. Okay. Now this is the multiplication principle, which means I have to put it together. I have to do 1 over my 52, and this time I'm going to multiply that by my 39 over 51, thus giving me 39 over 2652 as my result, and then reduce it or give its decimal answer. Okay. Any questions on that one? Let's do another one. Find the probability that from a standard deck of cards, you're dealt two cards, a king, and then another face card. So this is the same thing as before. We are looking for the probability that we get a king and another face card. So again, if we think about what this means, this is a conditional probability where we first are getting a king, and then we want another face card given that we drew the king first. Okay. So here, like before, we have to look at those two probabilities on their own. So first we want the probability that you get a king. So just like before, we have our fraction where your denominator term is your total, and there are 52 cards in the deck. How many of those cards are kings? Well, there's 4. We then need our conditional probability. So this one here is given that we are going to draw a face card, given that we are already holding the king card. So just like before, we look at your total. I'm already holding a card, so my total is 51. And I have to look at my face cards. Since there are 12 total face cards in a deck, and I'm already holding one of those cards, it means my numerator has to be 11. Okay, so again, this is another example of a double condition set onto your probability. Because we're looking for the probability that this happens, we simply have to put it together. So 4 out of my 52, we are going to multiply that by that 11 out of the 51. So here we get 44 out of the 26,652, and then reduce it or give me your decimal answer. Okay. So any questions over these two examples of a double condition probability using the multiplication properties? Okay. Suppose you like to keep a jar of change on your desk. Currently, the jar contains the following: 5 pennies, 27 dimes, 18 nickels, and 8 quarters. What is the probability that you reach into the jar and randomly grab a nickel and then, without replacement, a dime? So just like before, this right here, the and means multiplication. Without a replacement tells you what is going on. This one is a dependent event because I am holding on to the first coin I draw, which means the quantity or the total in my jar has gone down by 1. So here we are looking for the probability of getting a nickel and a dime. And so to do that says we have to first look at the probability of your nickel. And so that says, again, with my fraction, I have to look at how many nickels do I have in my jar. Well, I've got 18. And then I have to figure out my total. Since I didn't give you a total, it means you have to calculate it, and there are 58 coins that you have. The second probability you're looking for is the probability of your dime. And so again, you want to look at how many dimes that you have, and then you want to look at your new total. So here I have 27 dimes, but since I'm already holding a nickel in my hand, it means instead of having a total of 58, I've got a total of 57. Since this is the multiplication principle, the last thing that you would do is multiply them together. So this is 18 over my 58. And we're going to multiply that by 27 over the 57 to get your answer. And here you should get 486 over 3306, which you would then, as before, reduce or give me its decimal answer. Any questions on that one? Okay. So this here is going to kind of jump more over into the empirical idea, because remember, now we're talking about a population and we've got a table to work from. So there are 85 students in a basic math class. Right here, I just gave you a total, so that's the total that you would have to use regardless of anything else in the problem. The instructor must choose 2 students at random. What is the probability that a junior female and then a junior female and then a freshman male are chosen at random? So again, the buzzword here is the word and. And so we are looking at the probability where we are going to pick a female junior and a male freshman. And so when we're talking um, about choosing students to stand up. So if you think about where we are right now, if I were to choose one of you off of my list to say, turn on your microphone, as soon as I do that, now the pool that I have left to choose as a second person to turn on their microphone has gone down by one. This type of problem is a dependent problem in that that first choice you make is going to directly affect the choice that you can make as the second part. Okay, so you want to keep that in mind as you work it. And then we're going to do the same thing here that we did with our coins and that we did with our cards. And so we have to look at them as separate ideas. So the first thing we need to do is we need to know the probability of being a female junior. And so here, if we look at our fraction, the total number I have is 85. And then to figure out my female juniors says I have to come into my female column and I want to come to my junior row. And I'm essentially looking for the two places that this intersects. So if I think about my female column here, and then my junior row here, I'm looking for the two places where this occurs. And you can see right here on this number 4 is where these two are going to intersect. So my numerator here would be the 4. Okay. I'm going to use that same idea to do my male freshman, which again says I have to create my equation. Only instead of having 85 students to work with, I now only have 84 because I already have my female junior standing. And so I want to do the same thing. I have to look at my male column and I have to look at my freshman row. And the only place where those two come together is right here with this number 12. And so that would be your numerator value for that. To do your multiplication property simply says you're going to multiply these together. So 4 over that 85. And you're going to multiply that by the 12 over the 84. This is going to give you 48 over 7140. And then again, reduce your fraction or give me its decimal answer. Any questions on that one? Okay, here we go. A box contains 6 green marbles and 18 white marbles. If the first marble chosen was a green marble, what is the probability of choosing without a replacement a white marble? So again, this one is simply asking for a single probability. It wants to know the probability that you're going to choose a white marble. And this is going to occur given that something else has already happened. So for this one, the first thing you have to do is you have to calculate a total. And we do that by taking your 6 marbles plus your 18 marbles. And so here, this is going to give you 24 marbles total, and that's what you want to pay attention to. Now, the other thing that we know is that in order to calculate the probability of my white marble, this occurs given that my green one was chosen first. And so when we look at how to put it together, we need to take that into account with your denominator term. So here, when we would set up your probability, my denominator, instead of being 24, has to be 23 because I'm already holding a green marble in my hand. And the without replacement piece right here tells me that it is conditional. Now my numerator simply is how many white marbles are left, and there are 18. And so that would be all you need for this one. There is no multiplication piece to it because our question is only looking for the probability that we chose a white marble, given that you chose that green one first. So any questions with that one? Okay. This time we're dealing with 3 cards, but the idea doesn't change. You still have to look for what is the definition you're following, and then is it independent or dependent. So 3 cards are drawn with replacement. Right off the bat, this phrase here tells you that this one is going to be independent events. And what that means is that my total is not going to change regardless because I am putting the card back after I look at it. I want to know the probability that the first card is a club, the second card is red, and the third card is a queen. So here, that is what we're doing. We are looking for the probability of getting a club and a red and a queen. So just like before, we want to look at the probabilities of each individually. So we have the probability of getting a club is going to be found by 13 clubs out of the 52 in my deck. The second thing that I need is the probability of getting a red card, and that is going to be 26 red cards out of the 52 in my deck because these are independent events. The third is the probability of getting a queen. And this says there are only 4 queens out of the same 52 cards in a deck because, again, these are independent because we put the card back. So all we do here is multiply these together. This is 13 out of my 52. I'm going to multiply that by 26 out of my 52 and multiply that by 4 out of my 52. This is going to give me 1352 out of 140,608. And then again, reduce it all the way down or give me its decimal. This one becomes 1 out of 104 or give its decimal place. Okay. Any questions on that one? All right. These last two tend to be a little bit more on the tricky side because you have to be very, very fluent at reading your table and compare to what it is you want. Now, these questions are going to deal more with a range of idea, and so being able to identify what the probability is you're looking for versus what was your initial event and your conditional event is going to take a little bit of finagling. So you're going to be given this big giant table and it's life insurance. And so you notice we've got across the top life insurance of the husband, and then we have down the side life insurance of your wife. And notice that they are all in ranges. And it's talking about the amount of life insurance in thousands. And so that is what this table is given. So what the question says is, given the wife has between 0 and 50,000 of life insurance, what is the probability that the husband has between 0 and 150,000 of life insurance? And then round your final answer to 4 decimal places. So what we are actually doing here is we are finding the probability of your the husband's insurance given the wife's insurance first. So this is the condition that we are trying to find. And so in order to work it through, we have to first know the probability of your husband given the wife, and then we have to find the probability simply of the wife's insurance. Okay, so when we look at what we're doing here, we have to look at the whole. So we are going to first start with the probability of your wife. And this is going to be done differently. Instead of actually creating a fraction, we're using the table to get there. So the wife insurance is right here on this side. And so we have this entire row here that we are playing with. And so this is the row that we're going to look at for the wife's insurance. So she's between 0 and 50,000. So this means in order to figure out her probability, we have to take that 400, add it to the 200, add it to the 166, and add it to the 50. This is going to give the wife 816 as her value. Now, in order to do the husband, because that's going to be this side, here's the husband's insurance, we have to look at what his is specifically, and the husband has to be between 100 or 0 and 150. So when we're thinking about what part we're using, we are now using this piece right in here, where we have between 0 and 150,000. So these are the values that matter. So the husband given the wife's insurance would be 400 plus the 200 plus the 166. So his total would be 766. The conditional probability comes when you take those two things into account. So the probability that we are setting up is the probability of your husband given the wife's insurance condition over the probability of the wife's insurance. So here this would be 766 over that 816, which is going to give you 0.9387 as its probability. Okay. So any question on how we did this one? Okay. So let's do it one more time. Again, we've got the following table. It's got your insurance information in there. And the question says, given the wife has between 50 and 100,000 of life insurance, what is the probability that the husband has more than 150,000 of insurance? So just like before, we've got our wife's side that we are looking at here, and she's got between 50 and 100,000. So we are looking specifically at this row right here to be the wife's row. So when we're talking about the probability of the wife's insurance, we are adding that up. So we have 50 plus 50 plus 30 plus the 292. And this should give you a total of 422. Now, the second part is we need the husband insurance given the wife's insurance. And so again, when we are looking at the husband's side of things, we want that the husband has more than 150. which says the only value that does that is this more than 150 piece, which is just simply the 292. And so there's nothing else to add there. So when we put this probability together, it's going to be the same as what we did before, where we're going to have the probability of the husband's insurance given the wife's insurance first over the probability of the wife's insurance. So here this would be 292 over the 422. And then round it to 4 decimal places, so you would get 0.6919 as your result. Okay. Are there any questions over 9.3 using your conditional probability or your multiplication principle? Okay. 9.3 is what wraps up the probability part of this unit. So when we come back together on Tuesday, we will be starting in on section 9.4 and 9.5. This is going to be your counting principles section. You are going to want to make sure that you bring your scientific calculator with you to class, because we are going to be talking about permutations and combinations. And there are easy ways to calculate that using the actual probability commands of your calculator. And so you want to make sure that you have it so that we can go over what it is you're trying to do, and so that if you have calculator questions, you can ask at that time. So if there are no further questions over this or over anything we've covered so far, that is it. You are completely free to go and continue having a wonderful, fun day at home. Thank you.